So today we're going to go over 6.3. This is a pretty light section. This is just kind of like information and facts. Towards the end of this section, we'll do a couple practice problems that kind of just review what we talked about in 6.2, just to make sure you're on board with all of that. But 6.3 is basically some, basically just fact checking on domain and ranges. These are things that sine and cosine functions recycle themselves. And they have something called a period that every so often all the values repeat themselves in the sine and cosine and tangent functions. But you just kind of have to know what they are. And again, this is for the basic functions. So, you know, we're going to do things in 6.4 to 6.5 where we adjust all of this. Okay. But for now, this is what we're going to be working with. So something to keep in mind with sine is you can plug any angle into sine that you want. And so that means that all real numbers are fair game. But no matter what you do with sine, the outcome will always be between -1 and 1. So the range is between -1 and 1 inclusive, meaning you actually can touch -1 and 1. That goes the same for cosine. So as you notice, sine and cosine have identical domains and identical ranges. And in fact, the cosine is just a shift, a horizontal shift, sometimes called a phase shift of the sine function. So the tangent function, tangent of theta, is all real numbers except odd integer multiples of pi halves. And we'll talk about why that is in a second. So the range of tangent is all reals. So what I'd like to do real quick is I'd like to just kind of show you what this is talking about. So I'm going to show you a graph. So I have y equals sine of x, and I'm just going to graph this. And that's what the sine function looks like. Now you notice that it only goes up to 1 and it only goes down to -1. And all these places that it crosses the x-axis, those are our x-intercepts, where it has a peak or a valley, a maximum or a minimum. Those are also going to come into play in the following sections. So literally, if I graph the cosine function, it'll be the same exact graph, cosine of x, but this time it's just shifted. So it's shifted to the left pi halves. We'll figure out all of that in the coming sections. So these are basically sine and cosine are identical graphs, just one of them shifted around. Now what I want to do is I want to show you the tangent function, completely different. So the tangent function, we'll just do tangent of x. We'll graph this. And that is a completely different graph. So there are actually asymptotes at all of the hash marks, vertical asymptotes at all of the hash marks that don't have the blue line going through it. Those are actually the asymptotes that tangent can never touch. And that's because tangent is sine over cosine. And when is cosine equal to 0, we have to stay away because then we'd be dividing by 0. So cosine is equal to 0 at pi halves, 3 pi halves, 5 pi halves, 7 pi halves, 9 pi halves, all of those values. So that's why when we come over here and we say that tangent, you're allowed to plug in any real number except, or any real angle, except integer multiples of pi halves, because that's what would make cosine 0. So you got to stay away from those. Remember, cosecant is 1 over sine, so then you got to stay away from anything that would make sine 0, which is all the integer multiples of pi. Cosecant is a slightly different graph that has, or I'm sorry, a lot different graph that has a range from -infinity to -1, and then from 1 to infinity. So that means between -1 and 1, there is no value on this graph. And again, these are things we'll see in the coming sections. Secant has the same range, but it has integer multiples of pi half, or odd integer multiples of pi half because it's 1 over cosine. And then cotangent is all r's except for integer multiples of pi, because that's when sine would be 0, because cotangent is cosine over sine. So these are just kind of some facts that you should be writing down. Hopefully you've had a chance to go over those right now. If not, pause the video, get all these facts kind of in your notes about the domain and range. So remember we talked about the period of a trig function, or the period of a function is how long it takes for it to repeat all the same values. So for sine, we have a period of 2 pi, and for cosine, we also have 2 pi. So I want you to understand that sine and cosine are the same, and tangent, it repeats itself every pi. Now, again, this is just the base functions. You know, if you mess with it and start putting like 2 thetas and 4 theta minus 8, you know, all of this stuff, you start changing the problem, then obviously the periods will change accordingly. Okay. Some more information right here. And just to keep in mind, if I were to draw this graph, and let's say that I drew the sine function, and I'm trying to draw it so it's like the one that we looked on the, oh geez, that's bad. Right? So what this is saying is if we start here and we end here, this is one period. Okay? And that's kind of the standard. And then it will do it again right here. It'll do another period. So now this is another period. So if you went from here to here, that's actually 2 periods, okay? Or from here to here, right? Oops. You guys get the idea. Okay. So however long it takes for a sine function to repeat all of its values, or a cosine function or a tangent, secant, cosecant, so on and so on, that's called the period. Okay. Some fundamental identities that we'll need. This will be much more important. Not just these identities, but a lot of the identities will come into play much more heavily in chapter 7. So this is kind of an intro to that. So again, we know that the cosecant is 1 over sine, the secant of theta is 1 over cosine, the cotangent is 1 over tangent, and the tangent, another way to think of tangent, is sine over cosine. Remember, it used to be y over x. Well, you can also say that y is associated with sine and cosine is associated with x, so we can do that. And that likewise means that cotangent of theta is cosine of theta over sine of theta. Now this one I wanted to do with you. This is the Pythagorean identity. So the Pythagorean identity is sine squared theta plus cosine squared theta equals 1. And basically, if sine squared and cosine squared have the same angle inside, it really doesn't matter what's in there. It's always going to equal 1. And it's also very important that you understand that this is all based on the squared. It doesn't say that sine of theta plus cosine of theta is 1. It says that sine squared of theta plus cosine squared of theta is equal to 1. I want to rewrite this for you guys as well. It's very important that you also understand that this means the same as this. So when they square like that, that's just a notation that means the whole thing squared. So this is identical. There is no difference between these two. It's just a different style of notation. So I wanted to show you guys that you could take sine squared theta plus cosine squared theta, and you could divide everything by sine squared theta cosine, sine squared theta, and this equals 1, right? And then divide this by sine squared theta. Now this would cancel, and this would become 1, plus, now cosine over sine is cotangent, and 1 over sine is cosecant squared theta. So this is another identity that is built from this identity, okay? Now we could do it again, but instead of dividing by sine squared, we could divide by cosine squared. So I'm going to do sine squared theta plus cosine squared theta equals 1, but this time I'm going to divide by cosine squared theta, cosine squared theta, cosine squared theta. So now this means tangent squared theta plus 1 equals secant squared theta. So here's another identity that's based off the Pythagorean identity just by dividing. So these 3 identities come up over and over and over again, especially the original sine squared theta plus cosine squared theta just comes up nonstop in trigonometry, calculus, everywhere. So a lot of stuff can be built from that one identity. There's other manipulations we can do as well. We'll come back to some of those in chapter 7 especially. So now that we have a little bit of this information, if I wanted to find the tangent of theta, let's say that I gave you sine of theta is equal to the square root of 5 over 5, and the cosine of theta is worth 2 square roots of 5 over 5. Well, as long as I know the sine and the cosine, I can just do sine theta over cosine theta. But we know that sine of theta is square root of 5 over 5 divided by the cosine, which is 2 square roots of 5 over 5. But that would be square root of 5 over 5 times the reciprocal. And that would just be 1/2. So all that just to say that the tangent of theta is 1/2. Now we could do the same thing over here. We have the tangent of 20 degrees, which I don't know off the top of my head, but I do know that the sine of 20 degrees divided by the cosine of 20 degrees is just the tangent of 20 degrees. So that's just 0 degrees. Okay. Do the same thing over here. What is sine squared of 40 degrees plus cosine squared of 40 degrees equal? Well, I know that equals 1 because that's the Pythagorean identity. Doesn't matter what's in here as long as they match and it's sine squared plus cosine squared or cosine squared plus sine squared, it's going to equal 1. Okay. Let's look at even and odd functions. So hopefully you notice that sine and cosine have some behavior about reflecting across the y-axis and reflecting across the origin. As it turns out, the cosine function is the only even function of the 6 trig. I shouldn't say the only even. Of the 6 trig functions, the ones associated with cosine, or I should say cosine and secant, are the evens. So remember that secant is really just 1 over cosine theta, right? So then if cosine is the only even, then its reciprocal 1 over cosine is also even. And this is odd. And this is odd. So remember, odd functions mean that it's a negative of the original function. And even function means that when you put the negative in, I mean, that's not what it means, but this is how we justify it, is that when you put the negative into the function, it does nothing and it comes back the same as it was before. So these are just some little facts that, again, they just come up in random spots. This isn't like the end all and be all of trigonometry, but these are all little facts that you put together to help you understand harder problems, okay? Just some quick math right here. Let's do sine of negative 45 degrees. Well, we know that it's an odd function, so that means I can take the negative and put it out and just sine of 45 degrees. Now we know from the previous section that the sine of 45 degrees is actually square root 2 over 2, right? But then there's the negative in front, so there's that. Now, if I were to draw the unit circle and I didn't use the symmetry, I would have drawn my circle and I would have said, well, 45 degrees, negative 45 degrees is right here, right? And I would have done this, and I would have found out that it's square root 2 over 2, but since we're in quadrant 4, that means that the sign is negative. So I would have got the same thing, but just using this made me be more aware or make this a simpler problem for me. So the cosine of negative pi, well, I know that this is the same as the cosine of pi because cosine is even and the cosine of pi is negative 1, and I'm done. If I had done the unit circle, I would have drawn my unit circle, and I know over here is pi. So then if I go this way, right, that's negative pi. So that's negative pi. And what's my y and my x coordinate? My x coordinate is negative 1 and my y coordinate is 0. Cosine is associated with the x coordinate, so I got negative 1. But I could just use the fact that it was an even function and make the negative in a way just disappear because it didn't matter for this particular problem. Okay, so I want to talk to you guys about this. This is kind of a little review to make sure that you understand what you're supposed to know by now at this point. I mean, there's a lot more to it, but this is like a big one. This is like a test question. So it'll say, what if I gave you the cosine of theta is worth 4/5? And theta, we don't know what it is, but it's somewhere between 270 degrees and 360 degrees. It says, find the remaining 5 trig functions, remaining 5 trig function values for theta. So basically, I'm going to write this down. I'm going to write sine of theta equals, we already know the cosine of theta is equal to 4/5. They told us that. We're going to find the tangent of theta. Then over here, I'm going to find the cosecant of theta. Here, I'm going to find the secant of theta, and then the cotan. of theta, okay? So here's the thing. We know that we are in, we know that we are in quadrant 4 because they said theta, whatever it is between 270 and 360. So that means we're somewhere here, right? So I'm going to draw my triangle. Okay, so we're in quadrant 4. Now, here's kind of the thing. You take this triangle and you kind of bring it out. That's our theta. We don't know theta, nor will we need to know it, but we know that the cosine is 4 over 5, right? So we learned in the previous section that cosine 4 over 5 means the x value, which is 4, and the radius, which is going to be 5, okay? Remember we did, what was it? X over r, right? So that means I actually can find this side as well. So I just do 4 squared plus, let's call it y squared is equal to 5 squared. So this would be y squared is equal to 25 minus 16. So y squared is equal to 9. So then y is equal to 3. So then I can put a little 3 right here, okay? So now I should be able to answer any question they want. Sine is y over r. So this is now going to become y over r. So 3 over 5. Tangent is going to become y over x, or sine over cosine. So this would become y over r. I'm sorry, y over x. So that would be 3. Oops, I don't know why my 3 here isn't working. 3 over 4. Okay, and then we have cosecant is just the reciprocal, 5 over 3, 5 over 4, and 4 over 3. Now, if you leave this, you're actually going to get marked wrong because you have to think, which quadrant are we in? We're in quadrant 4. So that means this is actually, and again, I know it can't actually be a -3, but for the sake of reminding myself, I'm going to say that it's a -3 because we're going downward. So now we have anything with a y in it, anything with a sign in it has to be negative. Okay, so this has to be negative, this has to be negative. Cotangent and tangent both have sign in them, and cosine is positive, so a negative and a positive become negative. So I had to just finish this up, and this is a test question. You will see something like this on the exam, okay? Very important that you always graph. You should always graph where you think you are. That's a lot of U's. You should always graph where theta ends up. Based on the rules that they give you, okay? So I just wanted to kind of show you guys all of this. This is pretty straightforward stuff. And again, this problem right here, you really have to know this is going to come up. This shows that you know a lot about triangles, you know how to build them. This is a very important problem for the exam. Be sure to ask me if you have any questions about the homework or anything like this. But this is an important question for the exam. All right, thanks for watching this video, guys. This is just a short and sweet one. I'll send this out to you pretty soon.